afternoon, students. So in today's lecture we'll be discussing about magnetostatics. So this is the syllabus what you have in the fourth module, that is magnetostatics. So we'll start with BIOT-SAVART's law, right? And then we have magnetic field intensity. So have you heard this anywhere else? Yes, in the second module we had electric field intensity. So here we have magnetic field intensity. Then again here we have magnetic flux density. In the second module we had electric flux density, if you remember. Then we have ampere circuital law, then scalar and vector magnetic potentials, right? Then we have force and torque. Then we have magnetic boundary conditions. Like how we had in the third module, right? We had boundary conditions between two dielectrics, between a dielectric and a conductor and free space. So we have magnetic boundary conditions in this module, right? So we'll see what are the prerequisites. So this is the analogy. In the second module we had D is equal to epsilon E. This relation we had derived in the second module, where this D is called electric flux density. Electric flux density, and whereas this E is called electric field intensity. Correct. So here also we have same thing, and what was this epsilon? This was permittivity. And here also we have the same thing. So this is called magnetic flux density, and this mu is called permeability. I think everyone knows this. You have studied in basic electrical when you studied magnetic circuits, right? And this H is called magnetic field intensity. Magnetic field intensity. So this is the relation what we have, right? In this module, so we'll be discussing this one. So moving to the next slide. Yes. So before starting this module, you should know what is the curl of vector A. Anyway, we had discussed this in the first module, right? Curl of any vector. So the curl of vector A is an axial vector whose magnitude is in the maximum circulation of vector A per unit area as the area tends to 0, and whose direction is in the normal direction of the area when the area is oriented to make the circulation maximum, right? So this is the definition of, this is the equation for curl. So it is given by curl of A, or del operator cross A vector, is equal to limit surface tends to 0, closed integral of over length, this is not surface, over length, A dot dl divided by delta S in the maximum circulation, and this will have the direction also, right? Unit vector an. What is an here? It is normal to the area when it is oriented to make the circulation maximum, right? This is about the curl. Now next, coming to we had two types of multiplication in vectors. One was dot product and cross product, right? Here maximum will be using cross product in this module, so this one you should be aware. This is which coordinate system? We have rho, phi and z, so this is cylindrical coordinate system. and here we have r, theta and phi. This is spherical coordinate system. So these two are very important, right? So always this rho, I mean r, phi and z will be mutually perpendicular to each other. We discussed this in module 1, right? So when you rotate this towards this side, right, so the direction will be this one, correct? So when rho and phi is rotated, the resultant direction will be along z. So that is what is given here, right? So a rho cross a phi will be az, a phi cross az will be a rho, az cross a rho will be a phi. These three you have to remember, right? This is because all three are mutually perpendicular to each other, right? Similarly, if I write a phi cross a rho, this will be minus az, that you should know, right? And here, and this is for spherical coordinate system, we have ar cross a theta which is equal to a phi, and a theta cross a phi is equal to ar, and a phi cross ar is equal to a theta. And here what you have to note is, again, if you have the same component, like how we had for dot product, suppose we have dot product, ar dot ar will be 1, but here ar cross ar will be 0, right? Only when these two are different, you'll get the resultant. When both are same, it will be 0, right? So this you should note. So this is for spherical coordinate system. This for spherical coordinate system, yes. Moving on to the next one. So you should know this one also here. That is, this is the equation for cross product. Cross product of two vectors is given by multiplication of both magnitudes into the sine of angle between A and B, and this is given by AN, right? AN. So when I write B cross A, this AN will be in the opposite direction. So we'll have negative sign here. Right? That I think everyone knows, right? So we'll move on to the next slide. Yes. And mostly we'll be using curl here in this module, right? Like how we used divergence in second module, here we'll be using curl in most of the places. So this is curl equation for Cartesian coordinate system. You can note it down. In Cartesian coordinate system, this is the curl equation, and this is in cylindrical coordinate system. This is in cylindrical coordinate system, and this is in spherical. This is in spherical coordinate system. So you should note this for today's derivation. We will be using these, right, in some places. Yes, we'll start with BIOT-SAVART's law. Please read the definition here, statement of BIOT-SAVART's law. BIOT-SAVART's law states that the differential magnetic field intensity dH produced at a point P, as shown in the figure, by the differential current element IDL is proportional to the product IDL and the sine of angle alpha between the element and the line joining P to the element, and is inversely proportional to the square of the distance r between P and the element. Read the statement once more. Biot-Savart's law states that the differential magnetic field intensity dH produced at a point P, as shown in the figure, by the differential current element IDL is proportional to the product IDL and the sine of angle between and the sine of angle sine of angle alpha between the element and the line joining P to the element is inversely proportional to square of the distance r between P and the element. So now we'll understand the diagram. So now here they have placed a conductor. This is nothing but you can consider it as a wire, right? And in this wire the current flowing is of I amperes. Current flowing is of I amperes. Now we don't know what is the length of this wire. We don't know what is the length of this wire. So for the sake of analysis, we cannot consider the whole length from whatever is the length. We don't know that. So what we have to do is we have to consider a differential length. We have to consider a differential length. So differential length I'll consider like this. So of some length like this dl. So this is differential length. This is the differential length dl. Right? So now what will be the current through this differential element? Wire is the same, right? So the current has to flow here is also I itself. The current is also I, right? So now what all we have now? We had a wire which was carrying current here. So since we cannot take the whole length, we have considered a small differential length of dl, length dl, right? And the current going through that also is I amperes, right? Now if we want to calculate what is the magnetic field intensity at this point P, magnetic field intensity at this point P, according to BIOT-Savart's law, the differential magnetic field intensity is directly proportional to this current element, that is IDL, into sine of angle between the line joining the point and the current element and this current element. So that is alpha. That is alpha. Sine of this alpha, and inversely proportional to square of distance between the current element and the point where we are calculating the electric field intensity, which is nothing but r, and it has a direction, so it is a vector. It is a vector, right? It is in bold, so it is understood that it is a vector. Now we'll analyze once more. So first thing, we have a current carrying conductor. So just for the sake of analysis, we'll consider a small differential length here, and the current through that is also I, right? So this differential current element will be I into dl. Now according to BIOT-Savart's law, to find the magnetic field intensity, right? According to BIOT-Savart's law, so if you want to find magnetic field intensity at this point, according to BIOT-Savart's law, it is directly proportional to the current element, the magnitude of current element, that is I into dl, right, into the sine of angle between the line joining the current element and the point and the current element itself, right? So that is alpha. That is alpha, right? And inversely proportional to the square of the distance between the point and the current element, that is this distance. So if this point, if I take it here, what happens? The distance is more. So the magnetic field effect or the magnetic field intensity at this point will be much lesser than this point, right? So as the distance increases, the magnetic field intensity decreases. Now one more thing. Yes. So when this magnetic field intensity will be maximum? When alpha is 90 degrees. When alpha is 90 degrees, this will be maximum. That way we can know from this sine alpha, because sine 90 is 1, right? And ideal. So if the current is more, this magnetic field intensity also will be more. So now coming to the mathematical part. Yes. So now we'll write the equation part of the law. So the differential magnetic field intensity is directly proportional to current element, differential current element IDL into the sine of angle between the line joining the current element and the current element, and inversely proportional to the square of distance between them, right? So now dH will be equal to, if I want to remove this proportionality, I have to introduce a constant here, k into, and remaining everything will remain the same, ideal sine alpha divided by r square. Now where k is the constant of proportionality, so in SI units k is given by 1 by 4 pi, like same as our Coulomb's law, correct? So dH is equal to IDL sine alpha divided by 4 pi r square. So what we have done here, we have substituted k as 1 by 4 pi, right? So from the definition of cross product, I had shown the definition of cross product here. It is the magnitude of two vectors into the sine of angle between them, right? Into the sine of angle between them. So it can be written as, so since we have I as one part, dl as one more part, and since we have sine of two angles, right, we can write it as 4, I mean this we can write it as IDL as one part into AR, that is this direction AR divided by 4 pi r square, which is equal to IDL cross, how to write this AR? We know that the unit vector AR can be written as R vector divided by magnitude of R. So the same thing is written here. So IDL and this AR cap is written as R vector divided by R. R square was already there. One more R will make it R cube. So this is the final equation. This is the final equation. Right. So what you have to know here is, because of this sign we can introduce the cross product here, right? So that will be ideal cross AR cap. So this AR cap can be written as R vector divided by R. So R square into R will become R cube, right? So this equation you have to remember, IDL into R divided by 4 pi R cube. This is important, right? So now we'll move on to the next slide. Yes. So now where this is with respect to the direction. This is with respect to the direction. Now assume you're holding a conductor. You're holding a conductor in your right hand, right? Such that the current direction is in the direction of this of your thumb, right? So the thumb indicates the direction of the current, right? Then your fingers which is curled the conductor, so that gives the direction of the magnetic field intensity. The magnetic field intensity, the curl of your fingers will give the magnetic field intensity, where the thumb gives the direction of the current. If you hold the conductor such that your thumb shows the direction of current, then the curled finger shows the direction of magnetic field intensity, right? The same thing we can understand with the screw also. Now here a screw is placed, and if you rotate the screw in this direction, So in which way the screw advances gives the direction of current. Direction of current, right? And one more important part here, this is dot and cross convention. So when you mention the dot here, that means that means the current is coming out of your laptop screen or mobile screen, whatever you have. And if you have cross, the current is going inside the screen or the book, inside the book, right? Now see here, so if you hold the thumb here, if you hold the thumb here such that your thumb is pointing towards the screen, and the curled fingers will show the direction of this current, right? Because here we have written cross, here we have written cross. Cross means current is, or DH is inwards, DH is inwards. So if you put your thumb perpendicular to the laptop screen, and the curled fingers will show the direction of the current, right? So we'll move on to the next slide. Yes, like this is the next one, that is charge distributions. Like how we had, current distribution, sorry. So in second module we had charge distributions. If you remember, we had line charge distribution, surface charge, and volume charge distribution. Similarly, in this module we have current distribution, right? So the first one is line current. The first one is line current. It is given by this, it is shown here, right? It is shown here, line current distribution. So this is this you can take as a wire where the current is flowing. So how this is how we represent current charge distribution, I into dl, like how we saw in BIOT-SAVART's law, right? Dl. Now we'll move. Next one is surface charge distribution. So this is the surface charge distribution, right? So if you have a sheet, right, with the current like this, so you can see what is the current here. So that is given for the current charge distribution, it is denoted by k vector. K vector. Here it is IDL. IDL is for line current line current distribution, and this is for surface current distribution, that is K into ds. You have to remember this. And J into dV, this is volume actually, right? If you have a conductor like this of cross section, and if you want to know what is the current, then volume current in this particular volume, so that is given by J vector into dV. So what you have to remember is IDL is for line current, K ds is for surface current, and J into dV is for volume current. So these terminology is important, right? So same thing what we discussed in second module, right? Like for charge distributions. So moving on to the next one. Yes. Now this is what we derived from BIOT-SAVART's law. Correct. DH is equal to line current distribution IDL cross R divided by 4 pi R cube. If you want, you can just check here. So this is what we derived. This is what we derived from BIOT-SAVART's law. So take that equation here. Take that equation here. Consider that equation here. So we have DH is equal to IDL cross R divided by 4 pi R cube. So if you want to find only H, this is differential current in magnetic field intensity, right? So if you want to find H, how do you find? We need to put the integration here, correct, over length L, over length L. So what do we get here? We'll get I dl cross R, and whatever remaining is there, the same thing will be here, right? Only thing is we'll add one integration. So that will give you the line current distribution. You can consider this equation we have written from this equation. So just by adding an integration here, it will give me what is H, right? Now one more important thing. Now in the previous slide we have seen what is line current distribution, surface current distribution, and volume current distribution. So if you simply replace this by surface, that is K into ds, and when you introduce a surface integral here, remaining all the formula will remain the same. That will give you what is magnetic field intensity, due to this surface, right? Now next, if I introduce a volume integral, and replace that by J into dV, it will give me what is the volume current distribution, or what is magnetic field intensity due to volume current distribution, right? Now here what you have to understand is whatever we have written here is only with BIOT-SAVART's law, what we have seen earlier, right? So instead of ideal, I can put K into ds with surface integral, or for volume I should write this as J into dV over volume integral, right? Now moving to the next slide. Yes, like how we had determined what is magnetic field intensity, or sorry, what is electric field intensity due to infinite line charge, we'll obtain the same thing here for magnetic field intensity due to a straight current carrying conductor. Both are the same. So again what we'll do, so now consider this figure, please understand this figure properly, right? So this figure properly. So now first what you have to see here is we have a conductor like this of some length, right? Don't worry about the length here. We have some conductor placed like this, and the current through that conductor is I. So whenever you have a current carrying conductor, we know that there will be magnetic field produced around it, right? Now what we are doing is we are actually finding what is what is the magnetic field intensity, at some point P, where the perpendicular distance between the line and the point is rho, right? The perpendicular distance between the line and the point P is rho, right? Now we cannot take the whole length from A to B. For analysis. So we'll consider one small differential element dl. We'll consider a small differential length dl on the line, right? Now I'll draw one line from B to this point, and I'll draw one line from A to this point. Now whatever angle here we have from B to this point is alpha 2, right? And when I draw a line from the differential element to this point, the angle is alpha, right? And the line joining from A to the point P, the angle is alpha 1. Now what will be the coordinates of this dl? It is at the height z from the origin. It is at the height z from the origin. So this is origin. So this differential length is at the height z, right? So what will be the coordinates of this dl according to cylindrical coordinate system? So it will be 0, 0, z, 0 0 z, right? And what will be the coordinates of this point P here? It will be rho phi, again it is 0, since it is at the origin, z is also 0. So with respect to this thing, what is it, position vectors, how can we write this? So this will be 0 a rho cap plus 0 a phi cap plus z a z cap, correct, in the form of vector. So how can we write this one? It will be rho a rho cap. Now since we are calculating the effect here, you have to note that since we are calculating the effect here due to this conductor, so the arrow for this resultant length will be this one, like this, right? So final minus initial will be, what will be the coordinates of this one? Rho a rho cap. And what will be the coordinates of this one? It will be z a z cap. So final minus initial will be r vector will be equal to rho a rho cap minus final minus initial z a z cap. So this is the equation for r vector. So that is what we have written here. That is what we have written here, right? And what will be dl? Dl will be this length, right? And since it is taken on z axis, dl will take it as dz into az, because it is along z axis, correct? Now yes, so now we have understood how we got this dl, because dl is along dz direction, I mean z direction, so we have taken this length as dz, and since it is along z axis, we have taken this az cap. And we understood how we got this r also. R is equal to rho a rho minus az cap, right? Now look at the equation from BIOT-SAVART's law. We need I dl. Dl we got, I is I itself, and we have got r vector also. So we have to find what is dl cross r vector. Dl vector cross r vector. So when you see dl cross r vector, right, what do we have for dl? We have dz, az cap, cross what is r? We have rho a rho cap minus z az cap, correct? Now when we do this into this, we get az cross a rho. What is az cross a rho in cylindrical coordinate system? This we have seen in the initial slides. So here we can see az cross a rho is a phi. So here I can write it as, now dz and rho will be as it is, but whereas az cross a rho will be a phi, a phi cap, right? And similarly, when we multiply these two, az cross az, it will be 0, right? So this will be the equation for this one. That is what is written here, rho dz a phi. I hope everyone understood how we got this, right? Now substituting in this equation, take this equation. So if I want to obtain h, I have to integrate this. So I put this integration sign. This I remains I itself. So dl cross r, right? We'll write it as rho dz into a phi. Correct. So we have written here. Now this 4 pi r cube will be 4 pi. What is r cube? How did we get this? I'll show that now. Now we know that r vector, we got it as rho aero cap, minus z az cap, right? So what will be magnitude of z? It will be root of rho square plus z square. Now here we have r cube, right? So if I want to find the cube of this, it will be rho square plus z square whole power half into, power cube. So it will become rho square plus z square 3 by 2. So that is what is written here, right? So now, so we have understood how we got this equation now. So further solving this one. Now letting z is equal to rho cot alpha, right? So consider this triangle, right? So this is alpha, this is alpha. So what is cot alpha? Cot is 1 by tan, opposite by adjacent. So it will be adjacent by opposite. So adjacent is, so cot alpha will be equal to adjacent by opposite. So adjacent is z, opposite is rho. So z will be equal to rho cot alpha, rho cot alpha, right? This one. Now dz is equal to integrating this, differentiating this one with respect to alpha. What do you get? So you get rho will be constant, right? Differentiate d by d theta of cot theta will be minus cosecant square theta. So that is what is written here for dz, right? Now we have rho square plus z square whole power 3 by 2. So substitute the value of z here for z square. Z square will be rho square cot square theta, right? So 1 plus cot square theta will be again cosecant square theta. So we'll get this equation. So substitute everything here, and this integration we are obtaining from a to b, correct? So alpha will be alpha 1 to alpha 2. So alpha 1 to alpha 2. Solve this one. You will get minus 1 by 4 pi rho a phi alpha 1 to alpha 2 sin alpha into d alpha. So when you solve that equation, the final equation what you get is this one. Please, I want everyone to take your notebooks and try to solve this derivation, right? I have not shown all the steps here, but you will definitely get the answer when you solve step by step, right? Like how we solved for electric field intensity due to infinite line charge, the same way you have to solve this here, right? So we got h is equal to I by 4 pi rho cos alpha minus cos alpha 1 into a phi, right? This is the equation for this line from a to b. Now suppose if I want to derive this for infinite line charge, what happens? This b will be at infinity, right? So if b goes to infinity, what will happen to theta? Theta will keep on reducing and it will become 0. Alpha 2 will become 0. Alpha 2 will become 0, right? Now similarly, this b, this a, if I keep on pulling down to minus infinity, what happens to this alpha? So this alpha will gradually come to what to say 90 degrees, and then further if you move down, what will happen? It will become 180 degrees, right? So for infinite length, alpha 1 will be 180 degrees and alpha 2 will be 0 degrees. So substituting alpha 2 as 0 and alpha 1 as 0 degrees, this is the equation what you get. So this equation is for infinite conductor carrying current. So magnetic field intensity due to an infinite conductor carrying current, right? So this is for a finite length, this is for infinite length, right? I hope everyone have understood the derivation, right? So now going to the next slide. Yes, so same thing, we have magnetic field intensity due to a circular current carrying conductor. So first understand the diagram here. So this is the current carrying conductor which is in the form of loop, so the current is flowing in this direction. So we know that when you hold a thumb, right hand, so this indicates the thumb and this indicates the curl. So dh will be in this direction, and this dh is for rho direction. So here they are again decomposing what to say h into two parts, dhz and dh rho, right? So now due to this circular current carrying conductor, we are calculating the magnetic field intensity at this point, right? So what we'll do, we'll take this height as h, from the origin, right? So the coordinates of this point will be 0 0 h, right? Now again, this the radius of this circular ring is rho, right? Now again, the coordinates of this point is 0 0 h, and the coordinates of this differential length, again we cannot take the whole circle, so we'll take the differential length dl. So what will be the coordinates of this one? Coordinates of this one will be rho, phi will be 0, z also will be 0, right? So final minus initial, so it will be h az cap minus rho a cap. This will be r vector. Same thing, right? What we derived in the previous one. Same way you have to solve that. I hope you have understood the diagram. Now what will be magnitude of r? Magnitude of r will be root of rho square plus h square. Right? So with this knowledge we'll continue the equation. So yes, again we are taking the equation from BIOT-Savart's law. This is from BIOT-Savart's law. Now what we need is IDL cross r divided by 4 pi r cube. So r, as I told you, it will be h az cap minus a rho. So if you interchange that one, it will be minus a rho cap plus h az. That is what is written here, right? So this is r, and what will be dl? dl here, I'll erase this one. Yes. Now, so now how to determine dl? Now I'll draw a line like this. So the length of this line is rho, and the angle according to cylindrical coordinate system it will be d phi, right? So the length of this one will be rho d phi, correct, into a phi cap, a phi cap. So it is along phi direction. So this is the way how phi changes. So the unit vector is a phi cap. So this is dl vector, this is dl vector, correct. So now, yes, this is rho d phi, a phi. So we got all the values what we require, we are just substituting it here. Now dl cross r, dl cross r, so you know how to find the cross product of for what to say, cylindrical coordinate system. Please refer this one, please refer this one. Oh, this is curl, sorry, cross product I have not shown here, this is for curl anyway, that's not required. So curl, I had given the equations for curl, not curl, sorry, cross product. We have seen the equation for cross product for all the what to say three coordinate systems. So this is dl cross r. So here we have a rho, a phi, and az. So this is for what to say dl. Dl doesn't have a rho component and az component, only a phi component we have. So that will be 0 and 0. And for r, what we have in place of a rho we have minus rho. So minus rho is written here. Phi is not there, so phi will be 0. And z, in place of z we have h, so that h is written here. I hope you have understood. This is simple cross product, nothing complicated. So these are the unit vectors of that respective coordinate system, that is a rho, a phi, and az, right? So when you solve this determinant, you'll get rho h d phi a rho plus rho square d phi az, right? A rho component and az component. So dh, substituting it here, right? I remains I itself, 4 pi r cube. What is r cube? As I told you, r is this one. So r cube will be rho square plus h square. 1 by 2 will be already there because of the square root. So when I take the cube of that, it will be 3 by 2. So this will be for magnitude cube, right? So this is r cube. So r cube is written here, and this is dl cross r, whatever we obtained here. The same thing is written here. You need to take the book and solve, or else you will not understand, right? So please take the book and try to solve. So here, when you solve everything, this is what you get with respect to a rho and az. So you have to reduce this equation, you have to solve it by yourself. The final equation what you have to get is dh rho. No, here we are writing it in the form of, here whatever we get with respect to a rho when you solve, that will be dh rho, and whatever we get with respect to az, that will be dhz. So you have to solve this equation such that you get only two parts, something into a rho and something into az, right? So that something is dh rho and dhz. So when you solve that equation, when you solve for this hz, because we'll have only hz component here, this effect will be throughout due to full conductor, correct? Throughout full conductor the effect will be there. So the magnetic field will have to move only in this direction, that is hz direction. It will not move in rho direction. So h rho you have to take it as 0 here, dh rho you have to take it as 0. This is what we did for electric field intensity also. This part will become 0, so only this part you have to take and solve. So from this we have to obtain what is hz. So for hz we have dhz we have to solve. So here we have d phi. D phi is a limit for the integration, variable for the integration. So when you solve that, so phi varies from 0 to 2 pi. So when you solve this equation, you get h vector as I rho az divided by 2 rho z 2 into rho square plus h square into 3 by 2, right? So kindly solve this equation with all the steps and try to WhatsApp me. I'll just tell you whether it is correct or not. If you are getting it, if you are getting it properly, then obviously it should be correct because it is simple integration here and only with respect to d phi, right? So d phi, when we solve, what happens? We'll get 2 pi here, 2 pi and 4 pi will get cancelled, and here we'll get 2. So I rho square az divided by 2 into rho square h square power 3 by 2. Nothing much difficult here. So here only thing what you have to understand here is, here this rho component will be 0. Why? I'll explain you once more. Here, so this dl we have considered only here for the sake of analysis. I can consider anywhere on this circle, correct? So this line whatever I've drawn, I can draw it from anywhere on the circle to this point. Anywhere on the circle to this point, I can draw that line, right? When you draw multiple lines or in the equal intervals, you can see that when everyone is trying to push, when every line is trying to push this point, in which direction it will move? It has to move only in dz direction. It cannot move in dh rho direction because the current is same throughout the conductor and the conductor diameter also is same. So it has to move only in hz direction, not in h rho direction. So that should be taken as 0 here. That is why in the next step we have not solved. We have not solved for a rho, right? Only for az, right? When you solve that, this is the equation what we get, right? So we'll quickly revise what all we have discussed today. So we have seen what is curl equation. So we used these two here. So these were the prerequisites. So this one we used, and this cross product also we used here. So, and then we saw what is BIOT-SAVART's law, right? Three things you have to remember here. So differential magnetic field intensity is directly proportional to current element IDL into the sine of angle between the line joining the current element and the point where you are calculating the magnetic field intensity and the current element, right? Sine of angle between that, and inversely proportional to square of the distance between the element and the point where you are calculating the magnetic field intensity, right? From that we got this equation. So whatever derivations we did today, we used only this equation. And we calculated what is dl, what is ideal, and what is r, right? Based on that only we did all the derivations today, right? And this was the right hand thumb rule, where the thumb indicates the direction of current and the curl of the fingers indicates the direction of magnetic field intensity. So like how we had charge distributions, here we have current distributions, line, surface and volume. So based on that equations, then we started with magnetic field intensity due to a straight current carrying conductor. So first we did it for finite length, then we considered alpha 2 as 0 and alpha 1 as 180 degrees. So the line will be plus infinity to minus infinity. So we got this equation for magnetic field intensity, right? And we discussed what is magnetic field intensity due to a circular current carrying conductor. So that is, this is the equation what we got. So in all the cases we found what was dl, we found what was r, and we found the cross product of these two, and then we solved and then we proceeded with the derivation, right? So in the next class we'll discuss about Ampere's circuital law, right? So try to redo the derivations in your book, whatever I have explained you today, right? So we'll continue in next class, right? Thank you.